Alright, so this is level 3. So if you haven't watched level 1 and level 2, or if you don't know how to deal with the right table, I would advise you to watch the video that is at the top right of the screen. So that video deals with level 1 and level 2, which actually appears in most of the past papers. Alright, so given that, let's proceed. Let's go to level 3. Alright, so dealing with the question, they said 1 mole of pure hydrogen gas is sealed in a 1 decimeter cube container at this temperature. So they gave us the number of moles, right? So whenever they say a certain amount of moles is sealed, they just give you the initial moles. So they say it is sealed in a 1 decimeter cube container, so they gave us the volume, right? So they gave us the volume. So we have to always make sure that it's in decimeter cube. So the only place where you don't need to convert it into decimeter cube is in this formula where there's a number of moles of acid over a number of moles of base is equals to concentration of acid times volume of acid over concentration of base times volume of base. So only in this formula there is no need, but even if you convert it, there is absolutely no problem. Matter of fact, that's what I used to do. So only in this formula you don't need to convert it, but everywhere else make sure volume is always in decimeter cube and make sure mass is always in grams. So if you have kg, make sure you multiply it by 1000 so that it can be in grams. Alright, so they gave us the initial mole of hydrogen gas. They said it is sealed in a 1 decimeter cube container, which is the volume, and then the temperature does not matter in the calculation, only in the reasoning questions. So they said equilibrium is reached according to the following balanced equation. So they gave you the equation. Now they say it is found that 0.11 moles of iodine are present at equilibrium. So now they gave you the number of moles of this particular portion at equilibrium, right? So they gave us the initial of this, they gave us the amount of moles at equilibrium of this, right? So now I want you to be careful of something. So I'm not going to focus on this question, just look at the exam guideline and memorize the definition. So they said determine the number of moles of each of the following at equilibrium. So when they ask for the number of moles of each at equilibrium, notice that we have this one, right? So this is 0.11. Now you are not going to use the ratio to find this one. We can't. We only use the ratio when it comes to change. Literally, strictly, we only use the ratio when it comes to change. So even though this is one more question, another YouTube video that dealt with it, but I saw that my student did not understand it, right? Simply because it was not really explained. So for this to be easy, I'm going to draw the table, even though it's 1 mark, right? The table doesn't really require that much work, even though it's 1 mark, so that you can understand what I'm talking about. So they said determine the number of moles of each at equilibrium. So we need to find H2 at equilibrium, right? So let me just draw this. So here is a table. Let me just try one more time. So let's just do this. Okay, fine. So something like that. Okay. So let's just do this. Okay, so let's just draw a rough table. So this one is not something that you should present, it's just on the side for you to understand this. So whenever they give you something at equilibrium, then they ask for then the rest at equilibrium, make sure you know the change. I'll show you why. So we know that it's going to be rise, right? So ratio, then initial, change, and then equilibrium. I'm not going to use concentration because this is not yet those 7 mark or 8 mark questions. So let's just do this. So it's just a rough table. Okay, let me just draw this line on it for ratio. So something like this. Okay, so we know the ratio is just 2 is to 1 is to 1, right? So notice they gave us the initial moles of, let me see, rather, where is the initial mole? They said 1 mole of pure hydrogen gas. So they gave us the initial mole of pure hydrogen gas, right? So, which is just 1. So I hope it's not confusing with the fact that I didn't write this balance equation on top. So this is obviously for Hi, this is for H2, and this is for I. So we have the initial mole, right? And then when it comes to this table, we already know that the products haven't yet formed. At the beginning, they have not yet formed, so they're always 0. Now, let's just deal with this roughly. So now they gave us the moles at equilibrium, right? They said it is found that 0.11 moles of I2 are present at equilibrium. So they gave us the number of moles of that, 0.11. So now we need to find the change, right? We just say final minus initial. So the change here is positive because products always form, while reactants always decrease. Now, here, so now when we find the change, notice we have just used the difference to find the change. When we find the change, that's when we are allowed to use the ratio. right? So here, because the ratio is 1:1, it just means that here it's 0.11. And then now here, because it's 1:2, it means for me to get this one, I have to multiply by 2. So then this is going to be 0.22. So products always form, right? While its reactants decrease. So notice this is going to be plus because it's products that form, right? Matter of fact, this is supposed to be a negative, right? So when it comes to reactants, you always put negative when it comes to the change, right? So this one I'm just rushing because I assume that you know level 1, right? So that we can go to a new level which will be completely different. So reactants, the change is always negative, but product, the change is always positive, right? So 1 minus 0.22, you can also think of it as 100 minus 22, which should be rather 100 minus, yeah, so it should be 78, so it's going to be 0.78. So that's how it is. All right, great. So they ask for the number of moles of each of the following at equilibrium. They ask for H2, so we already have H2, right? This plus 0.11 is just this. So we have 0.11, right? So we have the number of moles at equilibrium. And then they ask for HI. HI, here you have to show them, okay, you don't really have to show them the working out, it's just 1 mark. But even if you show them there is no loss, you can just show them that it's going to be 1 minus 0.22. But honestly, even if you don't show them, it's just 1 mark. So you can just write the answer. So it's 0.78. So this is really understood without the table, literally. So I had to show you the table in order to show you that we do not relate them. We don't relate the ratios when it comes to the initial or equilibrium. We strictly relate the ratios when it comes to the change. Even in the higher levels that we're about to do, I will show you that it's still change, right? So let's just do this. Okay, so let's go higher. So we're done with this thing. We're actually going to use this information. Okay, so I hope it didn't confuse you. I just rushed there because it's done in the previous video. So now here I want to focus on a new level. So now they said the equilibrium constant is this, right? So they give you the equilibrium constant. So we have the number of moles of everything at equilibrium. Then they give you the equilibrium constant, right? So they said the temperature of the container is now increased to this, right? So it was 721, now it became 850. Then they said the equilibrium constant is that. So they really gave you a nice level here. So I'll show you something. So the equilibrium constant is now this. Okay, so let me see something. Do we need the previous equilibrium constant? Because this question says, is the reaction exothermic or endothermic? So I'm just going to show you something. Let me just see something. Yeah, so we have the previous equilibrium constant. So now notice equilibrium constant at this temperature was 0.02. But now when the temperature is increased, the equilibrium constant increased, right? So when temperature is increased, equilibrium constant is increased. So I want you to notice something. Whenever Kc is increased, it just means that the forward reaction was favored, because Kc is always the concentration of products over, okay, let me just write it better. I honestly don't want to focus on this, but concentration of products over concentration of reactants. Okay, forgive my handwriting, my attention is not here. So now, if Kc is increased, it just means this became bigger. If Kc decreased, it means that this became bigger. So the fact that it's increased, it means the forward reaction was favored, right? So now, this increase in temperature, what does it favor? Increase in temperature favors the exo, rather the endothermic reaction, right? Increase in temperature favors the endothermic reaction. So now notice that temperature is increased. I deal with this in my other videos. So notice that they say temperature is now increased, right? So it means the endothermic reaction was favored, right? So the endothermic reaction is favored and the forward reaction is favored because of this, right? So it just means the forward reaction is endothermic, literally, because notice, increase in temperature favors endothermic reaction. We also know that Kc became large, meaning that the forward reaction is what became large. So therefore, it just means the forward reaction is endothermic. Yeah, so I hope you get this. The main purpose of this video is not this, it's the next level. So I'll show you that. Okay, I fully explained your answer in that. Yep, you tell them that increase in temperature favors endothermic reaction, right? And then afterwards, you will tell them what you will say that KCS increased, meaning that the forward reaction is favored, right? Then you say therefore the forward reaction is endothermic. Okay, let's now focus on the biggie, the real stuff. So this is where my attention is.
Just before I continue, if you want to be tutored, whether it is online or physically, whether it is the situation where you're struggling in maths or whether it is the situation where you're good in maths but want perfection, take a screenshot or save these details. Whether you're studying Cambridge, which is the UK curriculum, or whether you're studying NSC, which is the South African curriculum, or IEB, or native courses which start from N1 to N6, or any curriculum you're doing no matter which country you're at, we offer tutorials. We've got lessons and practice sessions 5 days a week. We also give you tests once a week so that we can check your improvement.
Watch the video that is found at the end of this video in order to know the prices and the updated contact details just in case this ones have changed. Alright, let's proceed. Alright, so now notice they said, okay, let's read the question. They said calculate the mass of HI present at the new equilibrium at this. Ha. So they want the final mass, if we were to say so. So I'm going to explain this stuff. So why is this in a new level? In the previous two levels, you are always dealing with initial, right? 1 mole of something is stored in of this rather is stored in a container, right? So you are dealing with initial and then it reaches equilibrium. That's the previous two levels. The previous two levels you are given before the reaction started, and then you are given equilibrium. So I hope you memorize it. That the previous two levels you are just dealing with the initial, and then you are dealing with equilibrium. But this thing is a new level. Why? Because notice that you are now dealing with an equilibrium and then you're dealing with a new equilibrium, literally. So we have a previous equilibrium and a new equilibrium. That's what makes it the next level. So it's no more before the reaction and then equilibrium. It's now previous equilibrium, new equilibrium. So this is the new level. So let's deal with this stuff. So how are we going to deal with this? It's easy, it's not hard. So they said calculate the mass of this present at the new equilibrium, right? This is what makes it a new level. Previous equilibrium, new equilibrium. So I'll show you this also in the graphical form. So um, let's draw the table. All right, so I have drawn the table. So this is just going to be for the ratio. So this is for the ratio, and then this is going to be for initial. Let me just write initial, but just write initial. Then this is going to be the change, and then this is going to be the moles at equilibrium. Okay, so there is equilibrium, then there is concentration. So equilibrium, and then there is the concentration, right? C equals to N over V. All right, so this will be it. So I just remember that the ratio is just 2 is to 1 is to 1. All right, so that's what it is. Let me just write 2HI. So 2HI, even though it's not necessary, but it is helpful though. You should actually do it. So then this is going to be, we're just going to have that. Okay, forgive my arrows there. So this is going to be H2, and then we're going to have I2. So we're going to have I2. So this is H2. Okay, so they're all in gas phase, right? So you should also write the phase, but I'm not going to waste my time there. So we just know it's gas, gas, gas. All right, so now looking at this, now what you have to do in this level is that whenever there is a previous equilibrium and a new equilibrium, all that you have to do is that the previous equilibrium is your initial. Your new equilibrium is your equilibrium. So your previous equilibrium is your initial, your new equilibrium is your equilibrium. That's all, literally. So let's just do that. All right, so we have the previous, let's look for the previous equilibrium. So they told us that 0.11, they told us that 0.11 moles of HI are present, right? So 0.11 moles of HI are present at equilibrium, right? So that is the previous equilibrium. They said 0.11 moles of HI are present at equilibrium. So that was the previous one. So 0.11, right? And now remember our answers that we found. They said determine the number of moles of each of the following at equilibrium, right? So this is our previous equilibrium situation. So H2 was 0.11 and Hi was 0.78, right? So 0.11 and then here 0.78. So these are the moles at equilibrium, which we now take as our initial. Now what we need is also the new equilibrium so that we can find the change. So do we have anything containing the new equilibrium? Let's find out. So the equilibrium constant is this is the previous equilibrium. Then they said the temperature of the container is now increased to 850 K. The equilibrium constant is this. So they didn't give us the new equilibrium. They didn't give us the new equilibrium. They gave us the new equilibrium constant, meaning that this is like level 2, right, of the previous video. So meaning that you're given the answer this time. Every time the equilibrium constant is given, I would advise you to put x on the change, right? So notice that if this is x and this is twice as much as this, it means that this one will have to be half x. But then instead of putting fractions, to avoid fractions, my advice is if you see that it's that situation, then you would rather put 2x so that this can become x, right? So if this was 3x, you would literally put 3x so that this can become x, right? So now notice the forward reaction is favored, right? So it means that this is still your reactant and this is still your product. If the reverse reaction was the one that was favored, it now means that you literally have to take this as your reactant and this as a product. So what do I mean? If the reverse reaction was favored, it means that this one will now be minus. The change would have to be minus because it's now your reactant and this is your product. But they just made it simple. The forward reaction is favored. So therefore, this one is the one that is minus and the rest is plus, right? So we still take this as our reactant, this as our product. Remember, reactants always decrease and products always form. That's why the change is negative for reactants and for products is positive. So whenever it's previous equilibrium, then new equilibrium, you have to be careful. You have to know which one is favored. So now we're going to say, so in order to get the equilibrium here, we're just going to say it's 0.78 minus 2x, right? And then here it's just going to be 0.11 plus x. Okay, here's 0.11 plus x as well. Okay, so now we can write the concentration. So remember, we have the volume. The volume is the same, right? Even if there is a new equilibrium, the volume is 1 decimeter cube. So they made it much easy. So it means that C is equal to N over V. So it just means it's this thing over 1, right? It's 0.78 minus 2x all over 1, but it's still the same. So there is no need. So then they just made it easier. So this is plus x, then this is 0.11 plus x. So we have the equilibrium constant. We know that equilibrium constant is concentration of products, right? Concentration of products over concentration of reactants, right? But anyways, let me not waste time with this part. So let's just find the concentration of products. Matter of fact, you don't even have to write that formula. There is no mark for it. So there is a mark for expression of this. So let's see. So the product is I2, right? So I2, and that's the concentration of H2 and concentration of I2. Alright, so the reactants is Hi. So we're just going to say Hi squared, right? So Hi all squared. Alright, we are given the equilibrium constant for the new equilibrium, which is 0.9, 0.09, right? So 0.09, so we're just going to say 0.09. And then do we have this concentration of H2, which is just this part, right? So H2, alright, concentration of H2, which is just this part, but they're both the same. That's the funny thing. So it just means that it's going to be 0.11, okay, plus x. And then we're going to have 0.11 plus x. So they made it easier. So this is what we have. Let's just do this. And then we have this particular portion, which is 0.78 minus 2x. So that's what we have. Okay, so 0.09. So now we can solve for x. And it's not difficult because this is just going to be squared. All right. Alright, so now from here, notice that these brackets are the same, so you can just say 0.09 is equals to this bracket squared, right? So I'm just presenting an easier way to solve this. You can solve it any other way, right? So I just want to show you the advantage of doing this. Notice that this is squared and this is squared, so meaning that you can remove it by square rooting both sides, right? Because this thing squared and this thing squared is the same as everything squared. So then you'll end up having 0.09 is equals to 0.11 plus x, and then you're going to have 0.78. Okay, let's just do it a bit better. So 0. Like a matter of fact, let's just do this. So we've got 0.11 plus x. Okay, try to write it a bit better. So 0.78 minus 2x. So all you have to do is just to cross multiply, right? And when you cross multiply, it will be in brackets. You're going to have 0.09, and then you're going to have 0.78 because you are multiplying two terms, so they must be in brackets. And then this is just times 1, so it's 0.11 plus x. And then you just solve. So this is in brackets, so you just solve. Alright, so now because of a lot of work, you might feel like, you're done, but always refer to the question, always check if you have answered the question. So notice the question, they're asking for the mass of this presented in your equilibrium. So they're asking for the mass. So what we have here is not even the number of moles, it's just x. So in order to get the number of moles at equilibrium, we have to use this part, right? So it's going to be 0.78 minus 2 times that, so it's going to be 0.78 minus 2 times. So I hope you get it. I hope there is no confusion, right? We're just going to use this part because it's the moles of HI at equilibrium, right? So that is just going to be it. So it's going to be 0.78 minus 2 times x, right? Which was this stuff. All right. So let's just get the answer of that. So this is going to be 0.625, right? So, yep, 0.625. So we've got the number of moles. So the number of moles, which is that. So, rather, the number of moles is this part. Right, so we've got this as 0.625. So we need to get the mass. So, let me see something. So, for us to get the mass, notice that n is equals to small m over big M, right? So therefore it just means that small m is equals to n times m. It's not a must to do this first, or rather let's just do it the normal way. So we have the number of moles 0.625, right? So now this is going to be the mass, which is what we're looking for, over the molar mass. We want the molar mass of HI, so we have to look at the periodic table. Alright, so looking for the periodic table. So notice we've got hydrogen, right? The molar mass of hydrogen is just 1, right? So hydrogen is over there, right? It's just 1. And then, so of course, hydrogen is just the first element. And notice that iodine is 127, right? So the molar mass of iodine is 127. So this means that we are just going to say 127 plus 1, right? So it's just 127 for I, or rather even 1 plus 127, 1 for hydrogen, 127 for I, right? So that's just 128. So the molar mass is 128. So now we're just going to multiply, so it just means the mass is the answer of 128 times 0.0625. So I hope you got it. I don't think I need to go further. So just the answer of this, that's the final answer.
Alright, we have reached the end of this video. I have included a playlist of similar type of questions. If you enjoyed this video, please like the video and subscribe to my channel. Any questions you've got or any video you want me to create, please comment below. See you in the next video.